today to share my updates on dark messenger search at an accelerator experiment, aka DAMSA experiment. So DAMSA is a short baseline beam dump experiment that aims to detect light, dark sector particles, or agents like particles. And as we know that almost 27% of this universe is made up of dark matter, so understanding about them is a big question. And with this experiment, we look forward to answer some part of that big question. Talking about agents like particles, those are the unique kind of dark sector particle because they interact with observable universe through electromagnetic field coupling. So whenever they decay, they give their signature double photon with small angle of separation. So we can actually measure those two photons and reconstruct and understand and study about those agents like particles. But to study this kind of physics, we need the detector with a sensitivity range of 1 meter. But the detectors which we have right now, they are in the sensitivity range of kilometers. So we need a new detector. So here comes DAMSA with tabletop experiment setup and 1 meter baseline. It provides a perfect sensitivity range to study these kind of physics, which are extremely rare because of its nature. And DAMSA aims to detect agents like particle in this sensitivity scale range. So talking about my specific task in this particular project, I did computational section of work in this project. So I analyzed background and tried to optimize it. And if you see the detector itself, there is a target of tungsten, and this is the main source of your background and the signals. Right next to it, there's a vacuum decay chamber. It provides a background free decay volume for agents like particles to split into double photons. Right next to it, the red one is a LGAR silicon trackers that provides you charge readout and also helps you to trace the trajectory. And next to it there is a ecal cesium iodide electromagnetic calorimeter. You can understand it as an actual detector, so it measures the energy, and also it helps for the 4D reconstruction of your signal uh, after the event. So during the whole simulation process, we noticed our background were mostly electromagnetic shower, electron, positron, photon, and one of the major difficult background we observed was beam-related neutrons because they were chargeless, difficult to reject, and they actually mimic our rare ALP decay signal. So we have to do something. We wanted to reduce this background because this mimic our signal and reduces our signal sensitivity. So we came out with a unique solution of altering or changing the configuration of the detector setup itself. We noticed that these background were influenced or impacted mostly by the dimension of the target, the length and the width, and also the decay volume length, or you can say the gap between the target and your actual detector. So we altered these three parameters. We made 120 configuration with different values for this parameter and ran simulations 10 to the power 5 runs for each configuration and gather almost 12 million signal events and compile all those information and optimize using Pareto frontier optimization method and Poise significance metric approach to quantify the most suitable and optimal configuration that maximizes our forward photon counts while minimizing the neutron counts because our signal is a subset of our forward photon counts. So in the result, we can clearly see that the angular distribution of the backgrounds or the particles at the target exit look like almost similar, but when they reach to the detector, all the photons are forward collimated. The neutron are spread randomly. Electrons also are almost collimated forward, and the positrons are also randomly spread. Through the optimization process, we got the optimal configuration with the highest significance value to be the configuration which has the 77 centimeter gap and length of the target to be 15 centimeter and the width to be 5 centimeter. We can also visually validate our optimal result because the red box means your higher forward photon counts and the blue circle inside it means your lower neutron count, and in each of these three plots which represents all of those three parameters versus each other has a consistent of that optimal result shown. So from here also we can understand that our optimized result was is true. In conclusion, we can also make sense in a physics term of our optimal result that 77 centimeter gaps provide an enough space for those neutrons to deflect away and minimum neutrons to reach at the detector. 15 centimeter target length provides enough target volume to reabsorb any neutrons were produced and reduce the neutron count. And your 5 centimeter width provide less hadronic interaction and provide more forward collimated photons. In future, we're going to still work with this project. We're going to replace the electron beams with the proton beam and see what kind of changes it brings to your optimal configuration. Also, we're going to include in the customized physics list in GN force with actual signals itself, so we'll have more accurate data and our optimized results will have more confidence in it. Last but not the least, I want to thank Dr. Masum Singh for her computational advice in this work, my research advisor, Jehun Yu, for the physics inside of this whole experiment, Toja Roy, Gajendra Gurung for their feedbacks, and all the members in my group for their support and help. And I want to thank you guys for watching me this.